Okay, so I think we can start. So today we are going to continue from where we left last time. If you remember, last time we started talking about sparse Gaussian process, and we talked about primarily about low rank approximations for the covariance kernel. And the idea is, if you can do a low rank approximation somehow, in that case, the whole idea boils down to using the Woodbury matrix inversion lemma to reduce the computational cost from cubic in number of training data to something like n r square or r cube, where r is much less than n. So that is the fundamental idea that we talked about last time in low rank approximation. After low rank approximation, what we talked about, so the first thing that we talked about was low rank approximation, right? After low rank approximation, and in low rank approximation we talked about different ways of doing low rank approximation, starting from singular value decomposition, then basis function, and if you are using a special kind of basis function in the Fourier basis, then you call it spectral low rank representation. Okay. After low rank representation, we started talking about subset based approximation. Subset based approximation. And in subset based approximation, what was the idea? The idea was you will select a subset of the training data, and using those subset that you select, you write the covariance kernel in a special form, and the special form was kz, kzz inverse, kz transpose. So here the idea was that you write k or approximate k as kz, kzz inverse, sorry. Kzz inverse, and then you have your kz transpose. Remind me why or how did we discuss or establish that this is a valid approximation? By considering that my r is equal to n, and if my r is equal to n, this approximation becomes exact, right? So this is what we discussed last time also. What was the limitation of this? Was there any limitation of this method? The subset was selected randomly and your result is dependent on the subset you select. And so we started talking about pseudo input based Gaussian process, right? And that is what we did not discuss. So that is where we will start today. So in subset based GP, the trained GP is a function of the subset selected. Okay. And if you select it randomly, which is generally how it is done, then what happens is that your result becomes random. For every time you run it, your subset changes, your result changes, and it can change drastically. It's not like a small change. Okay. So to address this pseudo input based approach for GP was proposed. Okay. What is the idea of pseudo input? The idea is that you will assume that there are some other inputs apart from the training data, and finally those inputs can be your subset of training data or may not be, may or may not be. But you will assume that there are some additional input and you will try to optimize over that to select the optimal input. So those points, because you do not actually have output corresponding to those points, you start calling them pseudo input. Okay. So if you have to write the data, you have the training data, which is perhaps xi, ti, I equal to 1 to n. So this is your training data. And then you also assume pseudo data, du, let me write it, and zi, ui, I equal to 1 to r. And I am sticking to the notation of r because r is much less than n. That is our assumption, because without that assumption, the computational cost will not be reduced. Clear? Okay. Now with this setup, so T is coming from your GP. So rather, if I have to write it properly, I will say that T is equal to y plus epsilon, where epsilon is your Gaussian with 0, sigma square, and then you assume probability of y to be a GP with 0, k x comma x dash, you can write, or x comma x dash, and this is what I will write it as k y y. Okay, that is the notation I will use. Okay, and from there we already found out that probability of t will come out to be okay. Now if I have, let me write one more step here before I go to t. Assuming n training data, which is the case with x, your probability of y becomes equal to a Gaussian of y given 0, and this is what actually I will write kyy. Okay, not the above one is my kernel. So this is what I will write kyy, where this is k x comma x dash evaluated at n training data, right? Assuming n data point, this is what we have seen, and then we cannot work with y because y is not measured, so we work with marginal likelihood, which is t. So from here we have already derived all of this, so I am just writing the expression for a quick recap. N comes out to be t 0 k y plus sigma square I. These are things that we have already derived in the second GP lecture, right? We have already derived this. So now let us go back and recall that we have assumed now pseudo inputs d of u, and this d of u we assume comes from the same Gaussian process, correct? So now what is the definition of Gaussian process? It is a infinite collection of random variable, any finite number of which will have a consistent Gaussian distribution. So following that distribution, or following that definition rather, can I not write probability of t u, right? Because t is a finite collection, u is another finite collection, I can combine them, that becomes another finite collection, and that is again from the same GP, so this would follow the consistent Gaussian distribution. So this is equal to Gaussian over t u given 0 0, comma, k yy plus sigma square I, k yu, k yu transpose or k uy, and k uu. And this is the last thing that we discussed last lecture, right? Now remind me, someone can you remind me why k uu do not have a sigma square I? Why is there no sigma square I in the second diagonal term? We discussed it last time. Can you remind me? Why is there not a sigma square I with k uu? What is the logic? Because those are not measured. Those are just assumptions. And when something is not measured, that cannot have measurement noise. So as a result, we do not have k uu plus sigma square I. Right? So this is my joint distribution. Right? This is my joint distribution of t and u. Okay. Now, what are the unknowns? Unknowns. If someone has to list down what are the unknowns in this, what will you train for? What are the hyperparameters of this model? L sigma square, sigma p square. So L sigma square, sigma p square, the usual hyperparameters of Gaussian process. Anything else? The R you will decide, so that is not a hyperparameter. Anything else? Not U, Z. U are not measured, so Z. So Zi and Zi, how many Zi? R numbers of Zi. So total number of unknown becomes R plus 3. Now it is no longer a low dimensional optimization because your training data may be in millions, your R may be in 1,000. So you are now optimizing over a 1,000 dimensional space. So it's no longer a low dimensional problem, unlike the usual GP. Okay. So this whole thing is R plus 3. Okay. And we want to train for this R plus 3. So any idea how will you train for it? We have to formulate something and maximize or minimize that, right? So what will you train? What will you train based on? Any ideas? The maximum likelihood of D. That is the marginal. That is the only option, because that is the only thing we have observed. We can only maximize over something that is observed. And what is observed? Only probability of T. But if you directly try to maximize over T, what is probability of T in this expression? What is probability of T in this expression? Can you tell me just by looking at this expression what is probability of T? What kind of distribution it is? Let's start with that. Gaussian. Mean? Covariance? Is there any U in the whole business? So if you just write probability of T, then there is no U in this formulation. Then if there is no U, there is no Z. If there is no Z, how are you going to maximize or minimize over Z? So you need to reformulate probability of T such that it includes this KUU or KYU, this kind of terms. You need to reformulate this such that it includes those terms. Clear? So in Gaussian process, we train by maximizing the marginal likelihood. That is always the case. Okay. However, in this case, if I just write down the marginal likelihood, just from the expression, I will end up with a marginal likelihood which will not have anything to do with Z or U, which means that is not usable, right? So therefore, what we will do is we will derive it, and you will realize in the derivation process we will make some approximations to make it tractable. Okay. Okay. So probability of t is what we want to compute. So any idea how will you compute it? So that u comes into picture. Any idea how will you compute it so that u comes into picture? The starting point will be the two basic laws that we are always using, the sum law and the product law. Okay. So integration of probability t given u multiplied by probability of u du. Okay. Now remember that if you don't do any assumption and just evaluate this, you will get the exact one, which will not have any u or ku. Okay. So we will be making assumptions here or approximations here. Okay. So, but anyways, let's call it equation 1. Tell me what is probability of u? Probability of u, what is it from this expression, from this slide? Probability of u, what is the distribution? Gaussian with mean 0, covariance KUU. So it is Gaussian over u with mean 0, covariance KUU. Now the difficult question, what is probability of t given u? From this expression, again the same top one. How will you find the probability of t given u? Or what is probability of t given u? Have we computed that earlier? Where? Prediction. So what was the expression? Gaussian over t. Now the mean, right? Mean is k yu k uu inverse multiplied by u, right? Comma. Coming to the covariance, remind me what is the covariance? Predictive variance, the same kind of expression will come. K yy plus sigma square I minus k yu k uu inverse k yu transpose. This term is your small c. Remember the predictive distribution? This term is your small c, KUU is your capital C, Cn, that we wrote before. And then the other terms are as it is. So this is exactly the derivation that we did last Saturday, if I'm not wrong. In the practical class, when I took that extra class, that's when we did this derivation, exactly this derivation, but that was for some other purpose. That was for finding out probability of t star given t. Now it is to find out probability of t given u. Okay, this is fine. So now I'm going to arrange it a little bit. So this is equal to Gaussian t given, let's see, this term is like a coefficient matrix, right? Linear regression, this term is like a coefficient matrix. So I can write it as A transpose U or AU. Okay, so this let us assume to be A. So then this becomes AU. Okay. And coming to the covariance matrix, leave sigma square I aside. We don't want to touch it. Remaining term, apart from sigma square I, let us give it a name and let us call it lambda. Okay. So this one, this plus this whole term I'm going to call lambda. So lambda plus sigma square I. Okay. So can someone tell me why I separated sigma square I from the remaining terms? Any intuition? Can you give me some intuition that why is it that I chose to separate sigma square I from the remaining terms based on last lecture. That is the clue. Why do you think I separated out? What is the formula we are using always last time? Woodbury. In Woodbury, we want one term that is easily invertible, which will be my sigma square I. Okay? Clear? Till now, I have not done any assumption, by the way. I've just rearranged and named things. That's all I have done. Okay? So, now, okay, let me write it down where lambda is equal to k yy minus k yu k uu inverse k yu transpose. Okay? And this is exactly the predictive variance kind of term that we calculate. Okay? So now I have my ingredient. I have my equation 2. I have my equation 3. I can substitute equation 2 and 3 into equation 1. And that is supposed to give me my probability of t. Correct? So let us see. Substituting 2 and 3 in 1. What will I get? Probability of t is equal to integration of first term is t given u, that is equation 3. So integration of Gaussian t given au comma lambda plus sigma square I. Okay? The second term, Gaussian over u given 0 mean k uu as the covariance. Gaussian over u 0 mean k uu as my covariance and then du. Right? Tell me what is the result after doing this calculation. Probability of t is equal to, first of all, what will be the distribution? Normal, correct? Gaussian t. Now what is the mean? 0, because mean of mu is 0, so this becomes 0. Covariance correct, a k uu a transpose plus lambda plus sigma square I. Right? Now let us substitute a, because a is something we assume, that's the name we gave. So we will substitute a and you tell me what will you get. Gaussian t 0, what is a? A is k yu k uu inverse. K yu k uu inverse, then k uu remains, and then a transpose. So if there is AB, it becomes transpose, B comes first, A goes, so it will become k uu inverse and then k yu transpose. Right? Plus lambda plus sigma square I. Right? Now you can clearly see that k uu inverse and k uu will cancel out. So this two will cancel out. So you end up with Gaussian over t 0 k yu k uu inverse k yu transpose plus lambda plus sigma square I. So I have a quick question. Okay. If I write lambda in its full form, what do you think I will get after doing calculations? So lambda is also has some form, right? Which is somewhere written here, right? If I write it down, what do you think we will get? KYY plus sigma square I. Isn't that what we are supposed to get in the original case? So our derivation is correct, but we cannot do that, because if we do that, we are stuck with no u in the picture. Everything will cancel out. First point. And we want to find out u. So we will not do that. But if you do that, remember that it will cancel out everything and you will get whatever was the original thing. Okay? Which is of no use to us, at least right now. Okay? So now comes the approximation. So now, if I want to work in this form, what kind of matrix is lambda? Is it a diagonal matrix? Is it a full matrix? So can you tell something about the type of matrix lambda is by looking at the expression of lambda, which is here? Will it be a diagonal matrix? KYY, let's talk about it. Is KYY a diagonal matrix? KYY is what? Exponential at x comma x dash. That's a full matrix. Yes, the value reduces if things are in ascending order, but it's a full matrix. Correct? Which means KYY is a full matrix, KYU is a full matrix, everything is a full matrix. It is very unlikely the total thing will be a diagonal matrix. So lambda is not a diagonal matrix. So our assumption is that, or the modeling assumption that we do here is that we make lambda to be diagonal. We make lambda to be diagonal. And the question stands, why do we make lambda to be diagonal? From this expression, can you look at it and come up with some reason that why lambda we want to make it diagonal? Invert using Woodbury. So that lambda plus sigma square I will take it as A. And that inversion will be a total diagonal matrix, so 1 by 1 by 1 by. So the reason is we want to invert this at a reduced cost. And if we have to invert it at a reduced cost, we have to remember that lambda is a n cross n matrix. We have to make it diagonal. That is one way, obviously. There can be other ways also. So the modeling assumption here is that modeling assumption is lambda star. We model lambda star as lambda times I. Okay. And what is this notation? This is element wise product, Hadamard product. So that means there are two matrices of same size. You will do element wise product. And because there is an identity matrix, you will retain only the diagonals of lambda. Everything else will go to 0. Okay. So this basically what is it doing? It converts lambda to a diagonal matrix. Okay. So one philosophical question. Why am I using the term modeling assumption and not modeling approximation? This question will come a little bit later, but let me answer it now. So why do you think I am using the term modeling assumption and not modeling approximation or approximation? What do you think is the difference between assumption and approximation?
It might not be like a reasonably good estimate, like in some cases.
Here is no A, here it is lambda. What do you mean by A?
So there might not be a reasonable estimation in some cases.
Yeah, so can you elaborate on that? So that's the correct line you were thinking, but try to elaborate on that. So when we will say approximation, we will approximate. So we will try to minimize some metric or some divergence. Then we will call it approximation because we are approximating by, and we know that how good is our approximation. So we will try to minimize something. Here we are not minimizing something, we are randomly assuming something or imposing something. It is more about modeling imposition rather than assumption. So I'm imposing this to make my life easier. I'm not approximating anything. Is this correct? No, it is not correct. It's erroneous. And this will have an influence on my result. But why am I doing it? Because it's better to get some result than not get any result. Right? So that's why I'm using the term assumption and not approximation. Approximation will come in the next method. Okay? Okay, so we do lambda star, right? So with this, my probability of t becomes equal to a Gaussian over t with mean 0 and covariance I forgot. So let me see, kyu, kuu inverse, kyu transpose plus lambda star plus sigma square I. And this whole thing you can think of it as, I don't know, B maybe. Okay. Is it correct? Yes. Okay. And now there are two things we have achieved here. What are the two things we have achieved? First thing, my probability of t, which is going to be my loss function, will have u in or z in it. So it's now a function of z also. So, right? It's a function of z because kyu will involve k of x comma z. Right? So the first thing we have achieved is, so with this, p of t is a function of zi. And this is something we wanted, right? Because zi is something we want to estimate, which was otherwise not possible if we were not making some assumptions or approximations like this. Correct? What other thing have we achieved? If I have to invert the matrix, the cost will now be, I have to just invert kuu, or some terms which will be r cross r. So the second thing we have achieved is that inversion of covariance of t will now involve inverting r cross r matrix in place of n cross n matrix, right? And the second point I believe is, or should be obvious from last lecture, that if I have to invert it, what will be the formula? Can you remind me the Woodbury formula? A plus BUV or something like that, BUV whole inverse, right, is equal to A inverse minus A inverse U in bracket C inverse plus V A inverse U whole inverse A inverse V transpose, or V transpose A inverse. So the formula is, just to write it down, A plus UCV inverse is equal to A inverse minus A inverse U, you will get C inverse plus V A inverse U whole inverse V A inverse. This is the Woodbury matrix inversion lemma, right? Here our A is what? Our A is sigma square I plus lambda star, sorry, right? Inverting that is very easy because that's a diagonal matrix. 1 by 1 by will do in a diagonal, you will get that, correct? What is our U, C and V? Here, if you see, U for us is equal to K YU, right? C for us is K UU inverse, and V for us is K YU transpose, right? right? So now, when you invert it, we'll get reduced rank, and that we can use this formula to do that. Correct? Clear? So I'm not doing it, but the idea is that with this assumption, what is the assumption we have done? Lambda is diagonal. With that assumption, you are now in a position, you have a loss function, not this one, last slide, P of t, that you can maximize, or negative of log of that, which you can minimize. And by maximizing or minimizing, whatever is your choice, you can find out R plus 3 hyperparameters of your problem, R, where R is the number of inducing point, the pseudo points, and 3 is the usual hyperparameters. Clear? Okay. So now, with this setup, so by the way, what is the name of this method? This method is known as FITC. Okay? F stands for fully, I stands for independent, T stands for training, C stands for conditional. So fully, independent, training, conditional. Why independent? Why am I using the term independent? Lambda is part of covariance. We are making it diagonal, which means we are making it independent. Okay. Training, obviously during training we are using lambda. Conditional, there are conditional distributions where we are doing this because lambda is part of the conditional distribution. Right? So this stands for fully independent training conditional. So now can someone tell me how will the algorithm for this look like? I will not write it down, but I just want to hear. What will be the first step for this algorithm? What will be the input? What input will you have for FITC? What are the inputs you have? For any machine learning algorithm, what are the inputs? X and data. So your input is data. What you have to assume or to be known? The form of covariance. What else do you need? Number of pseudo points you are going to use. So these are your 4 inputs. Training data is given to you. You will assume some covariance form, and you will have to know how many R you are going to use. Right? Next step, what will you do? You will initialize, because you have to optimize. So you have to initialize your parameters. So you will initialize what? R, Zi, sigma P, sigma L. You will randomly initialize it. Correct? Now with those known values of sigma, you will find out the loss function, take the gradient, and based on the gradient, you will update the R plus 3 parameters. That's how you will go, and that's how you will find out everything. Clear? Okay. Okay. So this is the idea. Now, what is the limitation of FITC? I already told you. What is the limitation? What is the limitation? We are making a modeling assumption without any theoretical basis. Right? FITC assumes lambda to be diagonal. So this is like changing the model, right? I'm changing the model. I'm changing the model without any approximation or any loss metric or anything. Correct? Which will result in, this results in overfitting. Okay? This results in overfitting. Because you are changing the model, this results in overfitting, and you will see that your results may not match that well or as well as you want. Okay. So to address this, sparse variational Gaussian process was proposed by TTS in 2009. Okay. FITC was, I think, if I'm not wrong, was proposed in 2006. TTS, I think, TITSIAS, something like that, from University of Manchester, I think, came up with an improvement over that in 2009. Okay. We'll talk about the improvement, but before I go there, just by looking at the name, what are you expecting you will see here? The name is sparse variational Gaussian process. So what are you expecting? It has things that you have studied earlier in this course. What are you expecting? Gaussian process will be there, obviously. Anything else you are expecting? There is a new term I have introduced. So for that term, what are you expecting? Variational you are seeing, right? So what are you expecting? I've given you two clues. One is the term variational itself. And previously I said that we did not do any approximation yet. So in the next method, which is this method now, we will be doing approximation. So given these two facts, what are you expecting? We are going to use variational inference on GP to formulate sparse GP. We have discussed variational inference earlier. We are now going to use that on Gaussian process to formulate sparse GP. That's why the name sparse variational Gaussian process, right? So the idea is it uses variational inference to formulate sparse GP. And this is the pseudo input based GP. I mean, both of these methods can be classified as pseudo input based GP. Okay. So the problem statement remains the same. Problem statement is given data, we want to learn a GP model, right? This is the problem statement we are working with, to learn a GP, right? And this is also a pseudo input based approach, so we will have also assume this is also a pseudo input based approach, and because it is a pseudo input based approach, we will have du also, which is zi ui I equal to 1 to r, right? Clear? Okay. So now in Gaussian process training, what is it that we work with? What is the quantity that we try to maximize? In Gaussian process training, what do we try to maximize or minimize? Marginal likelihood. So probability of T is of prime importance. That you must have realized by now. Every lecture for last 2 or 3, whatever I am doing, I am going back to probability of T. So T is of prime importance because that is something you observe. And that is something you can operate on. That is the basis of the whole training, right? So marginal likelihood is of prime importance in Gaussian process, right? Now in this case, what are my models? Try to understand. Well, my primary model is probability of t. So think about it and tell me how I can write probability of t such that it involves t, y, and u, because these are the three quantities we are working with now, we are playing with. We are playing with t and y in the original Gaussian process. In the pseudo, we also have u. So whatever probability of t I want to write should involve probability of t, somehow u should come and somewhere y should come, and I should integrate over y and u. So can you think how should I write it? What is t a function of? T is equal to y plus epsilon. What is t a function of? Y. So the first term should be probability of t given y. Now I want to include u also in the picture, right? So that's why I will include probability of y given u and probability of u, and then I'll integrate over du and dy. I can do that, right? Clear? So now tell me, what is this distribution? What is this distribution? Gaussian with y comma, correct. Tell me, what is this distribution? Not so straightforward now. You know this, that is the clue, or you can find it out, that is the clue. What is probability of y given you? Maybe first tell me what is probability of u. Last method we use Gaussian with 0 comma KUU. Last example only we did it over u given 0 comma KUU. This is the only one remaining. Tell me. Clue. Use the definition of Gaussian process. So y and u are again from the same Gaussian process, right? Because t and y are from the same, and t and u, so all three are from the same Gaussian process, with slight modification in t, but y and u now no modification. So now you tell with that. So if y and u are from the same Gaussian process, what is the joint distribution of y and u? Gaussian with 0, and covariance will be yy, yu transpose uu. Now you from there you have to find out u given y. Same formula. What should it be? Mean. At least tell the mean. What will the mean? Open the go back to the what we derived just now. It is there. Y given kyu inverse multiplied by u. That is the mean. The predictive mean, that is the same thing. Kyu inverse multiplied by u. What is the covariance? Tell me. Kyy minus kyu inverse kyu transpose. So kyy minus kyu inverse kyu transpose. Right? So all three are Gaussian. I can now do calculation and find it out. Correct? But that's intractable. You cannot do that. It's of no use. And even if you do that, y and u will cancel out, and you will get what you were always getting from the beginning, which is of no use because that will not reduce the computational cost. So let me repeat myself. If we do this integration, what will you get? Without doing the integration, can you tell me? If I carry out this integration, what will I get? Gaussian of T, 0 mean covariance, KYI plus sigma square I. If I do this, that's what I am going to get. Because that is probability of T and nothing has changed. It's just another way of writing it. So just solving this integral is of no use. Because it will end up giving me a n cross n matrix. Full matrix I have to invert and that will be n cube, ordered, no use. It has no utility. Correct? So here comes the variational inference. Okay. So in sparse variational Gaussian process, we use variational inference that I have already mentioned. The second point is more important. Variational inference is used to approximate, and this is little bit tricky, this is not something that we generally approximate, to approximate probability of y comma u given t using or with q of u comma y. Okay. So this part is tricky. See it carefully. Generally, we find out probability of t given u or t given y. Our likelihood is probability of t given y. But here we are doing the opposite. Here for variational inference, we are taking t to the conditional part. And because u and y are unknown. Now this distribution is intractable, I cannot find it out. So I want to approximate it using some variational distribution. And that variational distribution is q of u comma y. Q is my variational distribution, that's the notation. Clear what I am doing? I will again repeat because this is something unusual. Generally, we work with probability of data given theta, right? Here I am saying that I am working with probability of theta given, theta is the unknown, theta given data. And I am trying to find that or approximate that using a variational distribution. Clear? The change is very minute, but it is clear. Okay. If you can understand this or follow this, the rest is just mathematics after this. Okay. So now we assume or we factorize q of y given u as follows. So q of y given u is there. We factorize that it as probability of y given u multiplied by q of u. So can you tell me can you identify that why this approximation is not so straightforward, or why, I mean, what is speciality about this factorization? The factorization I am done, what is so special about, is there something special about this factorization? There is one thing very special about this factorization. In the process of factorizing, I am using the true p. I am not writing qy given u, I am writing py given u. So that means, although it's a variational distribution, a portion of it I am going to use the actual one. The other portion is the approximate. So that means I don't have to find out q of y comma u, I have to only find out q of u, or rather the parameters of q of u. Because probability of y given u is the actual one that is known to me. That is the Gaussian that we wrote previously. Generally, I should have written q of y given u multiplied by qu, but I have not done that. I have written probability of y given u multiplied by qu. That means I am using the one factor is the true factor, other one is the variational factor, and the product is the variational distribution. Clear? Now with this setup, QU now I have to assume Q of U, and that we assume to be Gaussian. So where Q of U, we assume it to be Gaussian over U given mu star comma sigma star. Okay, clear? So what are the unknowns now? What are the unknowns with this after I have done this setup? What are we going to compute? What are we going to estimate? What are we going to estimate? What are the unknowns in the training process? Length scale sigma square are there. Anything else? Length scale sigma p square sigma square will always be there. Anything else? Obviously Zi will also be there, but because it is variational, now mu star and sigma star will also be there. Mu star and sigma star you don't know. So mu star and sigma star now has also come into your system. What is the value of this mu star? Who will give you that? No one. You have to minimize some KL divergence to find it out, right? So this is how you will proceed. You will first minimize the KL divergence to find out mu star and sigma star. Then use those mu star and sigma star to solve another optimization problem. So it's a looped kind of optimization problem where you will solve for the other hyperparameters. Okay. Okay. So the question is how to estimate mu star and sigma star. Any ideas? How can we estimate this? What should we do if we want to find out mu star and sigma star? Remember the name variational. What should we do? How should we find out mu star and sigma star? Mu star is sigma star are part of Q of U. Q of U is part of Q of y comma u. And Q of y comma u is supposed to be equal to or as close as possible to probability of y comma u given t. So then what should I do? KL divergence between Q and P. That's now it's variational. I'll repeat myself. I want my Q of u comma y to be as close as possible to probability of y comma u given t. That's the objective, right? I want my probability of y comma u given t to be as close as possible to Q of u comma y. Correct? Now in Q of u comma y, I factorize it as probability of y given u and Q of u. So the only unknowns is the Q of u. And I've assumed Q of u to be Gaussian. So the only unknowns are mu star and sigma star. So that means to find out mu star and sigma star, I should minimize some divergence, some metric between P of y comma u given t and Q of u comma y. Clear? So how to estimate this? By minimizing KL divergence. Okay. Now should we use the forward or inverse? Forward KL divergence or reverse KL divergence? Which one should we use? We can use both actually. But in this case, the name is variational. And in variational, we use the reverse. Okay. KL divergence, KL between Q, u comma y and probability u comma y given t. Okay. What is this equal to? Integration q of u comma y log of q u comma y divided by probability u comma y given t, and then du dy. Right? Clear? So now we will do some mathematical operations. That operation will include writing q u comma y in its factorized form, probability u comma y given t in its using the joint distribution, the Bayes rule or the product rule, and to simplify it. So we want to simplify it. So this is equal to integration q of u comma y, this will not touch, log the numerator. What is that equal to? Numerator, if I factorize, what is it equal to? Probability of y given u multiplied by q of u multiplied by q of u. The denominator, what is it equal to? Probability of u comma y comma t divided by p of t. Right? And what is u comma y comma t is equal to? Let me write it down step by step, not to. U comma y comma t divided by p of t du dy. Right? P of t will go in the numerator. So this is equal to integration q u comma y log probability of t or p of t, right, dot p what is it, I forgot, y given u, yes, y given u q u divided by, now the numerator, the remaining term in the denominator, how should I factorize it? How should I factorize that? Everything else has gone, only the p of y comma u comma t is remaining. So how should I factorize it? I have already factorized it earlier. How? T given u, t given y, y given u, u. We have already done that. So this should be equal to probability of t given y, probability of y given u, probability of u, and this will cancel out. And this is the main step we want. That's why we assumed that, because we wanted to cancel that calculation. And then you have du dy. Okay. So now p of t is my data likelihood. I'll separate it out. This is equal to integration q of u comma y log of pt du dy, and you tell me what is this equal to? What is this term equal to? What is this equal to? What is this equal to? Log of pt. We have done this because log of pt will come outside the integral. Other one is a PDF, so that integration will come out to be 0. So this is equal to log of pt. The second term, what will I get? Plus, I can also use minus, but let's use plus for now. Integration q of u comma y, okay, then log, what do I have? Q of u divided by probability of t given y, p of u. Q of u divided by probability of t given y, p of u. and then du dy. Okay, clear? So now what I'm going to do is that I'm going to introduce a negative sign. So this is equal to log of pt minus integration of q u comma y log probability of t given y pu by qu du dy, right? And what is the left hand side? What is this equal to? KL divergence, right? So therefore, if I take the second term to the right other side, what will I get? So therefore, log of p of t is equal to integration of q u comma y log p t given y pu by qu du dy plus KL divergence of q u comma y and p u comma y given t, right? Now what can you say about this term? Any property of KL divergence we can use here? KL divergence, what is the range of KL divergence? Greater than equal to, so this is greater than equal to 0, right? So therefore we have our elbow loss evidence lower bound, because left hand side is now greater than equal to the right hand side if I remove the second term. So therefore finally log of pt is greater than equal to integration of q u comma y log probability of t given y pu by qu du dy, right? Remember, this is the same derivation we have done earlier for elbow in variational inference, right? So now we will do some more simplifications on the right hand side. Okay, some more simplification because we want it in some certain form. So this then is equal to the right hand side. See, in the numerator there are two terms, right? We will separate it out. We will make it one term each. So this is equal to integration q uy log probability t given y du dy, right? The first term, see if it is making sense or not. Clear? What will be the second term? Plus integration q u y log what pu by q, I guess, pu by q du dy. You tell me what is this term equal to? What is this term equal to? Expectation, in terms of expectation. This is expectation of what? Exactly. This is expectation with respect to q u comma y of log probability t given y, right? This is log expectation of the log. Clear? Coming to the second term. So therefore, okay, this is it. This is equal to then expectation with respect to q u comma y log, what is probability of t given y? What is this distribution? What is probability of t given y? Normal. So you will get a convolution of log of normal with respect to normal. Not log normal, log of normal. Okay. And we'll come to that later. But let us finish what we are doing. The second term will be equal to, see, how many integration are there in the second term? 2. I mean, actually many more, because u can be vectored, but at least one is with respect to u, one is with respect to y. Now see, what the terms inside the log are only function of u. So, however, q is function of both u and y. So that means q u comma y is the only term that will be integrated with respect to y. And what will you get if you integrate that with respect to y? Q of u. And that will convert it into a KL divergence. Okay, so I will do that. So integration log, maybe I will write a negative sign here, wait, to make our, to do a step jump and write a negative sign here. Log, yeah, QU by PU integration Q u comma y dy du, and this integration will yield q of u, right? That's the property, marginal, the sum law. So then you end up getting, this is equal to then exponential q u comma y log, what is probability of t given y? What is the actual distribution? Gaussian, 0 mean, no, y mean, sigma square I as the variance, the likelihood. That is the log of the likelihood. The same term from first lecture, minus integration of, this will give you QU, so let me write QU log QU by PU du. And what is this term equal to? KL divergence between QU and PU. So therefore we end up getting expectation q u comma y log Gaussian t given y comma sigma square I minus KL divergence of QU and PU. Okay. The first term can be further simplified. Okay. I have 2 minutes, and 2 minutes is all I need, because I'm just going to give you the expression. So, and you try to derive it. This term, if I write it in expanded form, what will I get? Integration log of normal t given y comma sigma square I, right? That is the first term, multiplied by q of u comma y. What is q of u comma y? What is q of u comma y? Probability of y given u multiplied by q of u. So this is equal to probability of y given u multiplied by q of u du dy. This is nothing but q of u comma y, right? So now this is equal to then integration log Gaussian t y sigma square I multiplied by, what is y given you? Y given you is a Gaussian process. Multiply Gaussian, y given k yu k u inverse u, comma k y minus k yu k u inverse k yu transpose dy. This is integration over y, and then there is another integration here, and that is over qu du. See inside the square bracket, what do you have? Convolution of a log of normal distribution with respect to normal. Okay. Now convolution over normal with respect to normal gives you normal, and you know the formula. Convolution of log of normal with respect to normal, we have not done it. So I am just giving you the result of this. So this will come out to be, so this integration of log of normal t given k yu k u inverse u, comma sigma square I. So the mean will be, as it happens in convolution of Gaussians, the covariance will not change. Okay, qu du. So this is basically coming out to be expectation with respect to qu of log normal t given k yu k u inverse u, comma sigma square I. Okay. So what is our final loss? The last equation. The final loss is coming out to be one expectation term with respect to qu log of normal t given k yu k u inverse u, comma sigma square I, minus KL divergence between qu and pu. Okay. So this is the final expression, final loss function that you will minimize or maximize, depends, because it is the evidence actually, right? So and by doing that you will find out what? Mu star and sigma star. Once you have mu star and sigma star, you will plug those in and then optimize for the length scale parameter and other hyperparameters. Okay. So this is the elbow loss, evidence lower bound optimization. This is used for finding or computing the variational distribution, which is basically this, and then you will, from there you will estimate hyperparameters and also the inducing point, by the way, hyperparameters and z. Okay. So ultimately this derivation is for your understanding. You will use only the last term. Okay, you will use only the last term. This one you will maximize it to find out the mu star and sigma star, plug those in, and then find out maximize probability of t to find out sigma p square, sigma square, L and Zi, right? So that is the overall stochastic variational GP. Okay. So we are done with GP mostly. Next lecture we will start with unsupervised learning. That will be one lecture on that. And then we will go to neural network, which is the last part of the course. Okay. Saturday, 99% there will be class. I will send an email after booking the room. Okay. But Saturday is Friday routines, I think. So there will be no, so I cannot take this Saturday, but one Saturday will be class, I don't know when. So maybe I think 7th or 8th there is one Saturday that time. Okay. Thank you.